Hi, I'm Matt, and this is my Lab 3 Black Hole and Orbits video. Introduction: the purpose of the lab was to simulate the orbit of a black hole and determine the mass, and to also simulate the orbit of a spacecraft around a planet and moon, try to get a figure-8 orbit. The main physics principle used here was the law of gravitation, universal gravitation, and the outcome was that the simulation was able to determine the mass of the black hole with some variation, and that I was unable to achieve a figure-8 orbit. Just to go over some important principles and equations. So the first was the law of universal gravitation, which states that the force between two objects in space is equal to the universal gravitation constant multiplied by their two masses, all divided by the distance squared between the two objects. Some other formulas used in the simulation were the velocity update formula and the position update formula. And then another important principle was that net force, the sum of the forces, is equal to the sum of the forces perpendicular to motion added to the sum of the forces parallel to motion. Assumptions and setup of the lab. One big assumption was that the black hole was so massive that any forces acting on it were negligible, therefore it could be stationary in our model. Same thing with the planet in the second part, so the planet was much larger than any other forces in magnitude, so again it could stay stationary, and delta t was small enough in our simulation that it was accurate at modeling a constantly changing force. Here's my glow script code for part 1. The main concept used here was that F net is equal to F perpendicular plus F parallel, and you can see that demonstrated from lines 174 down to about line 186. Basically, we split the force F net into F perpendicular and F parallel. We have the calculated mass of the black hole, and then on the right we have the diagrams showing the forces. So the orange force is the net force, the blue arrow is the perpendicular, and the purple arrow is the parallel. So as you can see, if you were to add the two vectors together, you would achieve the orange vector. The orange vector pointing the net force, which is directly at the black hole, and then the blue vector being perpendicular to the direction of motion. The method for attaining the mass was, again, the law of universal gravitation, and then as you can see, if you manipulate the equation, given that we know what small m is and we know what the force is, then we can calculate the mass of the black hole, which is denoted by big M. And then the changing mass values is due to the changing distance. As you can imagine, the force would decrease as the radius increases. Here I have the code for part 2 of the lab. Basically from line 76 to line 97, I calculated all the forces acting on the ship and the moon, which was basically all the other objects in the system, and this was important in modeling motion. Here we have the analysis. I was not able to get a figure-8 orbit. The picture on the right is the closest I could get it to a figure-8 orbit, and we have the ship speed listed above. Because the planet mass is so much larger than the moon mass by several orders of magnitude, it's very difficult to get a figure-8 orbit because the planet's force is dominant on the spaceship. So if we don't want the spaceship to crash into the planet, we need it to move very fast, and then that is obviously well above the escape speed for the moon. Some possible sources for error. The method of simulation is iterative, so it's not actually reflective of a constantly changing force. We have delta t, and then we've simulated the changing of position by small increments of v average, which we calculate to be from some of the equations in the beginning of the slideshow. This causes the values to be slightly different than they would be in reality. And then another possible source is that the black hole in part 1 and the planet in part 2 are both stationary, when in reality that wouldn't really be the case. But this is an okay assumption because they are much larger than anything else in the system by several orders of magnitude. Analysis questions. Think about what rate of change of momentum means and what net force means in terms of things you can observe and measure. So the rate of change of momentum is really how fast something is speeding up or slowing down, and the net force is the sum of the total forces acting on an object, so force is perpendicular and force is parallel. What does this mean? Imaginary system, etc. All the forces on all other subjects would need to be modeled if we really want a very accurate computational model. And then the black hole is definitely the dominant force in the system because it is much larger by several orders of magnitude. In conclusion, the computational models are largely accurate, and a figure-8 orbit is probably not achievable.